Hello, everybody, and welcome back to Geography 341, Weather and Society. I am Dr. Zach Hilgendorf, and in today's lecture, this lecture here, we're going to be talking about some starting definitions. So as we touched on in the syllabus and introductions lecture, the purpose of this video is to kind of give you the tools and reference point to understand some of the terms that you're going to be needing to use when it gets to your weather journal and really just with the course. We're obviously going to touch on these definitions and really expound upon them once we get to that material, whether it's week 3 or week 12. But for the purposes of having you start to understand how to talk about weather, we're going to go over some fundamental terms and concepts. So the first of those fundamental terms should seem like an interesting one. What is weather? You're taking a weather course, Weather in Society. It is the short-term state of the atmosphere at a given place. That's really all it is. It is in opposition to climate, which is the characteristic long-term pattern of weather at a given place or in a given region, or the statistical properties of the atmosphere at a given place or in a given region. So weather is, if we think of this on long-term trends, weather is the noise and climate is the average. There we go. So here you can see all of these. If we think of these, this could be years and years, or maybe every minute or every hour. These are weather observations. Obviously, on purpose, I have the axes blurred out here so you don't actually see what they are, just because this is just to kind of illustrate a point. So weather is the average. So this is maybe, we're looking at a historical outlook of weather on January, what was today? 23rd, as of recording this, dating myself here. This is every year across 10 different cities over the last 50 years. Cool. That is the average climate. That line would represent the average. Likewise, if we look here, this is the kind of the temperature on the left, so temperature in degrees Fahrenheit on that top one, precipitation in inches in the bottom. This is from a NOAA website. I could not switch the units to metric, so we just have to deal with this. But you can see that these are long-term temperature averages in the or sorry, not long-term. These are temperature averages for the year. So we can see starting in January for this is 2022 through August, when I grabbed this image back in August. And that's our average temperature throughout each day. So every day is plotted on that. But if you notice above, that's our high temperature in the red above it, and our low temperature in the blue below it, and the green is kind of the middle sweet spot. That's the average temperature. So if we look at these 2 points, these are showing us just the weather, what's going on, the temperature and the precipitation. But if we look at these 2 parts here, that's the average. That's our climate for the year. So that just kind of shows, one is short-term, one is long-term average. Then we get into the study of meteorology. That is the study of the atmosphere and the processes, physical and chemical, that produce our weather. Whereas climatology is the statistical analysis of weather data to identify trends in what's going on in a region or a globe. And it's the study of atmospheric processes that produce characteristic long-term patterns of weather. So if you took my climatology, Geography 340 in fall, you learned all about climatology and a little bit about meteorology, especially towards the middle third to later third of the course. We're going to focus a lot on meteorology and a little bit on climate, because climate tells us what we could expect for weather at a given place. So we're going to need to understand how a lot of these things are described. So time, as weird it is to define time, When you're looking at weather readouts and weather maps, it's usually defined in 24-hour time, and it's usually in UTC, or Coordinated Universal Time. Zulu time is another way to call, or another word for that. So you might see it 1800 UTC, and that's in reference to the time relative to the Greenwich Mean Time, where basically the prime meridian is. So that's usually how we look at time regarding weather. So from an analysis of meteorological conditions to make a forecast requires measurements made at the same time over a wide area, including multiple time zones and possibly the whole world. That's why we use this format of time. So using UTC simplifies and standardizes that process of keeping track when each measurement was made. So that's something we'll have to get used to. We'll likely see most of our recordings in, especially if you're using things like Weather Underground or even NOAA, or weather.gov, or NWS, the National Weather Service websites. You'll likely see it in relative local time. But if you're looking at bigger, broader patterns, it's definitely going to be in UTC or Zulu. Typical units, as I mentioned, we're using metric. In fact, we're using System International, basically standard scientific measurement. So units in meteorology are a mixture of SI, or System International, units used throughout scientific meteorology, and older systems of non-SI units retained because historical reasons, especially here in the US, for convenience or for communicating with the general public. Because 32 degrees Fahrenheit for freezing and 212 degrees Fahrenheit makes so much sense relative to 0 degrees Celsius and 100 degrees Celsius, but we won't belabor that point too much more. But we'll be using primarily SI units for this, so metric and associated units therein. Energy is really important to talk about. We'll really dive into this next week, but energy is the ability or capacity to do work. It is a measurable quantity. That is a calorie, so the thermal energy needed to raise the temperature of 1 gram of water 1 degree Celsius, or a joule, abbreviated J. The energy expended by a force of 1 Newton acting over a distance of 1 meter. These are a couple different ways that we look at energy. We can relate those two. 1 calorie equals 4.19 joules. 1 joule equals 0.239 calories. So energy is really important. And within energy, there are a couple different forms, primary forms of energy and other forms therein. Kinetic energy, here, includes the motion of waves, electrons, atoms, molecules, substances, and objects. Potential energy is the stored energy and the energy of position. We've got radiant energy, the electromagnetic energy that travels in transverse waves. Radiant energy includes visible light, X-rays, gamma rays, and radio waves. Light is one type of radiant energy. Sunshine is radiant energy that provides the fuel and warmth that make life on Earth possible. Super, super important for us. They've got thermal energy, or heat, is the energy that comes from the movement of atoms and molecules in a substance. Oh, accidentally advanced here. Apologies. Geothermal energy is the thermal energy within the Earth, for example. Mechanical energy is the energy stored in objects by tension. Compressed springs and stretched rubber bands are examples of stored mechanical energy. And then we jump over within the forms of potential energy to pressure energy. And this is a really, really, really important one. Pressure energy is the energy in or of a fluid due to the applied pressure as force per area. We have a fun relationship known as the Bernoulli principle, which we'll talk about when it actually comes down to talk about energy in those lectures, which drives pressure energy and relates it to potential energy. But for now, for these purposes, we think of things like pressure systems. That's what drives our weather patterns. That's what drives wind. If you have a very strong high pressure system that is related to the distribution of heat across the planet and how these molecules are excited and moving, you have a high pressure system and a low pressure system off, there's going to be a pretty big, what we call pressure gradient force, or difference between the high and low pressure. So the wind is going to be really high and really kicking in those areas. So understanding pressure is very important to understanding how weather patterns are driven. We mentioned temperature. Temperature, we will use sometimes Kelvin to convert things, but primarily degrees Celsius. It's a non-SI unit here, usually used to quote temperature in general use, more readily understood, and values in convenient ranges. 0 degrees Kelvin is negative 273.15 degrees Celsius. You can get Kelvin by taking the degrees in Celsius and subtracting 273.15. You can get the degrees and temperature by multiplying the degrees in Celsius by 9/5 and adding 32. And you can, if you isolate any one of those in just some quick algebra, you can figure out how to get Celsius from Kelvin or Celsius from Fahrenheit. Air temperature, or really what is air temperature? Well, simply put, it is a measure of the average kinetic energy of randomly moving gas particles. What we feel as colder temperatures is really air particles that are not as excited than you'd see in warmer particles. We can see these 3 GIFs here on the bottom. The left GIF is an example of a colder air mass with slower moving particles, while the right GIF is an example of a warmer, more excited air mass. And the GIF in the middle shows, my script here, the GIF in the middle shows how a thermometer works. Those air particles collide with that thermometer. The energy is transferred to the mercury within, expanding the mercury, which we can then read as a temperature value. So just to give you an idea of like what is temperature and why we feel hot or cold temperature, it's related to how excited those particles are, those gas molecules are. Surface air temperature, what is surface air temperature? That's a really complicated question, because given the variability just across the surface of our planet, you have to have some parameters to standardize what those measurements are. We can ask what the air temperature is at 1.2 to 2 meters above the surface. We could ask about what it is in the shade. We could ask about whether it's over natural or artificial ground cover. Really, temperature can vary drastically across our surface. One tool that we use to get more accurate measurements of ambient conditions is a Stevenson screen. First developed by a Scottish civil engineer, Thomas Stevenson, in the mid-1800s. To use a Stevenson screen, you need to be at an air temperature of 1.2, you're getting the air temp at 1.2 to 2 meters above the surface. You see this box is designed to shade the probe, and you are over natural ground cover, not pavement, for example. Fun side fact, he was the father of Robert Louis Stevenson, who many of you may know if you've ever read or seen the book Treasure Island or The Strange Case of Dr. Jekyll and Mr. Hyde. That was his dad. So the Stevenson screen is a small weather station that is used to measure local weather conditions. It protects the temperature sensors from being directly influenced by direct or reflected sunlight, hence the box. They're always painted white because white has a high, what we call albedo, so it reflects things much more effectively than a black surface does. So it's not, the temperature isn't being altered by the coloring on the box. The louved sides allow airflow, outside airflow to flow around the thermometers. And then at some locations, the airflow is assisted by a psychrometer motor that pumps outside air across. You can see part of that motor sticking up. Got my little pen here, right here. It's a very poor arrow, but you get the idea. Looks kind of a little bit like a horn on the top there. One of these Stevenson screens will include a thermometer for maximum and minimum temperatures, a hygrometer for wet and dry bulb thermometers. So basically we're getting at humidity, dew point. Outside the Stevenson screen, there'll be normally going to be a rain gauge, likely a tipping bucket rain gauge, an anemometer for getting at wind, a barometer for getting at pressure, and a wind vane for getting at wind direction. And you can kind of see some of those in the back. There are a whole slew of different things set up here. And I advanced my slides, so we can sorry about that. Recording on PowerPoint, so you can't actually go back unless you re-record the whole thing. It's kind of goofy. But there were wind vanes and meteorological towers set up around that Stevenson screen, I'm guessing to validate the measurements within the screen itself, and to get a wind speeds a little bit higher above the surface. Moving in now to atmospheric pressure. Pressure is just the average force per unit area. So we're looking at air pressure in the free, uncontained atmosphere. So average force per unit area exerted on a random or by randomly moving gas molecules bouncing off of a surface. The units we typically think of, a few different ones. We look at pounds per square inch, newtons per square meter, or hectopascals. So 100 newtons per square meter give you a hectopascal or a millibar. So those are kind of the primary ones that we really look at. We'll talk a little bit later on how to convert between the two of them. So looking at atmospheric pressure units, the SI unit of pressure is the pascal. Atmospheric pressure is quoted in hectopascals, or hundreds of pascals. So 1 hectopascal equals 100 pascals. Pressure is frequently quoted in millibars, or MB. So that's our non-SI unit. 1 MB equals 1 hectopascal. It is a 1-to-1 conversion. And then we think of things like mean sea level pressure. This is something important. So all pressure is standardized relative to the mean sea level pressure. Mean sea level pressure is 1,013.25 millibars, which in hectopascals is same, 1,013.25. In pascals, it'd be 101,325 pascals, or 101,325 newtons per meter squared. So just to get the general idea there of how to convert between these different units. Wind. What is wind? Well, it is basically just air that's moving horizontally for the most part in the atmosphere. There are updrafts and wind can move vertically as well, but as we measure it, we don't necessarily measure the vertical component of wind when we're measuring winds on the surface. So we measure it, is it coming from any of the cardinal directions, or which direction is it coming from? And that is on a two-dimensional surface. So we measure it in the horizontal perspective. It's caused by a pressure gradient force that's pushing air from areas of high pressure to areas of low pressure to equalize the difference in pressure. So wind is really just the expression of horizontal differences and atmospheric pressure. So we'll learn a little bit more, I think, in week 4 or 5, I'd have to look at the syllabus, on winds and pressure differentials. But we'll get there when we get there. So continuing on with the definitions, wind speed, typically this is viewed in meters per second. That's our SI unit, all scientific use and frequent common use. Knots, or nautical miles per hour, so roughly equals 0.5 meters per second per knot. Kilometers per hour, kph, so 0.278 meters per second is a kilometer per hour, and then miles per hour, mph. We typically, I grew up learning wind speed as. So a mile per hour is equal to 0.447 meters per second. So we'll typically use meters per second or kilometers per hour, depending on what we're looking at. For the weather journal, I have you using kilometers per hour. All right, now wind direction. So this is the meteorological convention to give the direction that the wind is coming from. The big thing that people often misunderstand is that if I am saying that there is a north wind blowing, it does not mean that the wind is coming or blowing towards the north. It means that the wind is blowing from the north. So the bearing is in degrees from north. So a lot of times you are starting at 0 and going to 360 degrees. So that bearing starts at north. So just as a common reference point, gustiness is often only generally quoted, so northerly, southwesterly, etc. But here on the next slide, I'll have a diagram to show you. But just note that wind direction, if I'm saying that there's a north wind or a south wind, that means that the wind is blowing from the north or blowing from the south. It does not mean that that's the direction it is moving towards. So let's look at a diagram here on the next slide. So here we can see the wind direction here is being quoted at 50 degrees from north. 50-degree wind, we've got a northeast wind. That doesn't mean that the wind is blowing towards the northeast. That means that the wind is blowing from the northeast. So the mean wind vector is coming from the northeast, blowing towards the southwest. But we've got a northeast wind. So if we're saying we have the easiest way, if we have a north wind in the winter, it's probably pretty cold. So that might be an easy way to think of it, because we've got this big Arctic plunging air coming down from the jet stream, which we'll learn a little bit more about as we go further on. But yeah, so just keep in mind when we're talking about wind, we're not talking about the direction it's blowing towards. We're talking about the direction it's blowing from. So that should be hopefully helpful and useful. Humidity is the often given as a percentage. Relative humidity is what we're going to be focusing on primarily. It's the water vapor content of the air as a percentage of the maximum possible saturation or equilibrium vapor pressure content at that temperature. Don't worry, it's 100, so you're getting the percentage there, multiplied by the vapor pressure divided by the saturation vapor pressure. We'll get into that in a little bit. The measure is most closely related to our comfort. How humid it feels is really what we're getting at here. Relative humidity is telling us how humid it is. If it is, I don't know, 85 degrees out with 85% relative humidity, you're really uncomfortable because it is just humid and muggy and crappy. If you're in the desert, I lived in Phoenix for a number of years, the Phoenix metropolitan area, and I can't tell you how many times I heard, oh, well, it's a dry heat. And they were right, because we're in a desert, our moisture content in the air is so much lower. Our relative humidity may only be 10, 15% or less. Really dry air. But so is my oven, and I don't like sticking my head in it. So you can give an idea of how I felt about living in a desert for 4 years. But it's interesting because at different times of the year, that does feel very, very different. So we'll talk about temperature and humidity a lot more in the next couple of weeks. These are ones that are oftentimes, I think people don't often think about or understand too well. Dew point is the temperature at which a parcel of air with constant vapor pressure content must be cooled at constant pressure in order to become saturated. So think of it this way. Air temperature is always going to be higher than the dew point. The closer the air temperature and the dew point are to one another, the more humid it feels, and the higher relative humidity you calculate. If there is a much larger difference between the two of them, that usually correlates to drier temperature or drier feel. The dew point depression is just the difference between the temperature of a parcel of air and its dew point temperature. Dew point does not change with the temperature of air, but it does change with pressure. It decreases at about 1/5 the rate of the lapse rates for temperature, which we'll talk about once we get into kind of atmospheric stability in, I think, week 4. So don't worry about that for now. Just know that that is what the dew point is. Next, some biometeorological indices. That's just a fancy word for saying things like how we feel the weather. Heat index. That's our apparent temperature. It's basically an approximation of how hot it feels. the combo of air temperature and relative humidity give us our heat index. Warmer temperatures at a higher relative humidity feel hotter than lower or the same temperature at a lower relative humidity. That's where that notion of it's a dry heat comes from, because the relative humidity is so much lower, so it doesn't feel nearly as hot until it gets up a little bit warmer. There again, think of the phrase, it's a dry heat. Dry heat feels very different. And one of the best analogs, in May and early June, it might be 100 degrees in Phoenix. You do not feel it. If you think about that, that's really just a couple degrees higher than our average internal body temperature. But when you add that moisture content, that relative humidity, the heat transfer starts to feel a little bit different between you and the outside world. So it would be no problem to be out hanging out in 100-degree temperatures in mid-May in Phoenix because it just didn't feel hot. But here in Wisconsin, if you have a 100-degree day, that's almost always coupled with some disgustingly humid days in July and August. So it feels very different. So just thinking of that, that's heat index. The kin to that is wind chill. That's the portion of cooling of a human body by air motion. Basically, it accelerates the rate of heat transfer from the body to the surrounding atmosphere. We feel wind chill mostly in the winter or late fall when these really, really, strong winds are blasting across us. It's already cold, and it's basically wicking the moisture out of our pores, and it's feeling much colder than it actually is. One of the stories that I would always tell people that when I was living down in Phoenix was the time I was walking to campus when I was a student here at Eau Claire in my ice fishing gear and multiple layers because it was 50 below with the wind chill. And it was, I think the ambient temperature was 40 below, and then we had the wind on top of it. That was one of the coldest days I think I've ever experienced in my entire life. And with the wind chill, it only made it worse. So just a fun little analog there. And I have to have Cold Miser from Year Without a Santa Claus for those of you who know the story. But I digress. You most prevalently feel this below 7 degrees Celsius or 45 degrees Fahrenheit. That's when you really start to notice wind chill. Because if you're just blowing hot air around in the middle of the summer, it still feels hot. There's no chill to it. So you mostly feel this once you get down to the lower temperatures. Length scales. So this is an interesting one because we often don't think about this. So here we're looking at a satellite image of our planet. So satellite imagery reveals the scale of weather systems and their distribution with latitude. We can see things like cyclonic systems by these huge curved arms of these clouds in the mid-latitudes, low cloud amounts in the tropics, and this band of deep convection near the equator where you're seeing tons and tons and tons of clouds down that way. But there's a huge discrepancy between horizontal and vertical scales. So in a geography class, scale is incredibly important. The changes that happen vertically are drastically different than those that are happening horizontally. So if we're looking at local or micro scale meteorology, this is looking at a few hours to a day. Whereas our distance is only good up to around 2 kilometers. And the phenomena that we're looking at might be local convection, small cumulus clouds, fog, hill or valley drainage flows, or variations in surface wind. Now, if we move up to the mesoscale, the regional scale, this might be looking at hours to days, whereas the distance might go from few to several hundred kilometers. The phenomena here that we're looking at is thunderstorms, fronts, or land and sea breezes. And then we move up to our large scale or synoptic scale meteorology. This is looking at forecasting. So think of this on the scale of tens of days, from distances from hundreds to several thousand kilometers. And the phenomena here, we're looking at the movement and migration of massive high and low pressure systems that are really driving these changes, and kind of driving the local patterns. So to recap in this one, we talked about time, units, energy, temperature, pressure, wind, humidity, dew point, heat index, wind chill, and length scales. In the next video, we're going to be talking about historic weather. And then we're going to actually break into the real start of our content in the next week. But that one more video will be all we have for this week. So I will see you in the next video and hope you have a great day. Thank you.